Let's start with problem number 1. And I have a little introduction to problem number 1 that I want to start with. If I have here what we call a set of parallel capacitors, point A, point B, and VA minus VB, let's call it V, higher here than there. And this capacitance is C1 and this capacitance is C2. They both see the same voltage. What always holds that C of I, which is capacitor I, always has a charge Q of I on it if the voltage over that capacitor is V of I. This you can always use, it's always true. Now both capacitors see the same voltage over them. So therefore the Q of 1 equals C of 1 times V, and Q of 2 equals C of 2 times V. And in this particular case, where the two are parallel, they have this in common, and the Q's are clearly different because the C's are different. That's called parallel. If now we go to series, here we have two capacitors in series, C1, C2, point A, positive potential, point B, let's call it 0, negative potential, and again, VA minus VB is V. Now, there's something very important I want you to appreciate. This part here has no net charge, because as you connect this to a battery, no electrons are supposed to jump through this vacuum. It is true that this side becomes positive of the capacitor, therefore this side becomes negative by induction. It is true that this side becomes negative, and therefore that this side of the capacitor C2 becomes positive, but the net result here must be that the net charge negative here must exactly cancel the positive charge there. That is very characteristic for series. Therefore, Q1 equals Q2. The charge on here is the same as the charge on there, because charge left is charge right and charge left is charge right. So now we have Q equals C1 times V1, and we have Q equals C2 times V2, and now these two are the same. And so now, as you can see, since C1 is not the same as C2, the potential difference over C1, which is V1, will be different from the potential difference over V over C2. So here, essential is that the Q is the same in each case, but not the potential difference. If you work this out, then you could easily show that V equals that Q times 1 over C1 plus 1 over C2. And this is often called 1 over C equivalent. The C equivalent is, so to speak, replacing these two. If you had a parallel set of capacitors, then that C equivalent would become C1 plus C2. And I'm sure you will have no problems proving that. So let's now go to problem number 1 and apply some of what I just told you. So here we have point A, positive, C1, C2, rather complicated, C3, this point is called D, C4, and here is B, which is minus, and the potential difference VA minus VB equals V. And now one of the questions is, what is the charge on each of these capacitors? The first thing I'm going to do, I'm going to replace these two by an equivalent capacitor. 1 over C1 prime, equivalent capacitor would be C1 prime, equals 1 over C1 plus 1 over C2. And then I'm going to replace all three by an equivalent capacitor, which I will call C prime. And so we now have that C prime equals C3 plus C1 prime, which you just calculated. And so I have now reduced this circuit to an entirely different circuit. I have now here C prime, and I know how large C prime is. Then I have C4. This point is D, this is A, and this is B. Check for yourself, this is exactly what the circuit is now. And if you go back to my introduction, then the Q on C prime must be the Q on C4, two capacitors in series, and therefore I will call this Q. And so it's very easy to calculate for you now what VC prime is, the potential difference over here, because C of I equals Q of I divided by V of I, and it is also very easy for you to calculate what the potential difference is over number 4. Now, let's go back to the original scheme. We have here A, and we have here C1, and we have here C2, and we have here C3. This is point D. Okay, let's leave it as it is now. This is between A and D, and I just leave 4 out for now. There is a 4 here, I realize that. I want you now to concentrate on this part. And that part is exactly what I covered in my introduction. Therefore, Q1 must be Q2. The charge on here must be the charge on this one. And I would like you to, I leave you with the problem, because you do know what VA minus VD is. You know that because we just did that only 30 seconds ago. So you can calculate now the charge on here, and you can calculate the charge on there. Q3 equals C3 times the potential difference between A and D, which we just calculated. I want to remind you that the potential difference between A and D is nothing but the potential difference over that C prime. So you know VA minus VD. And so you can calculate now charge here, charge there, and you can calculate charge there. And I will leave you with that. I don't think there's too much more to this problem. Rather straightforward, but they can be a little nasty.